Welcome back, everyone. We're glad you're here with us. Imagine discovering a world that breaks every rule we thought we knew about planetary survival. A place that should have been consumed by fire, torn apart by cosmic forces, reduced to nothing but stellar dust. Yet there it is, orbiting peacefully, as if the laws of physics simply don't apply. 530 light years from Earth, NASA's instruments have found something that challenges everything we understand about how planets live and die. It's called 8 Ursae Minoris b, though astronomers have given it a more fitting name, Hala, the impossible planet. What do you believe could survive the death of a star? Share your thoughts in the comments. Now, let's journey to a world that rewrites the story of planetary survival. Chapter 1: The Impossible Discovery. On a quiet afternoon in 2018, deep within the sterile halls of the Space Telescope Science Institute in Baltimore, a computer screen flickered with data that would challenge everything astronomers thought they knew about planetary survival. The signal was subtle, a rhythmic dimming of starlight so faint it registered as barely more than statistical noise. Yet, buried within those gentle fluctuations was evidence of something that violated the fundamental laws of stellar physics. The Transiting Exoplanet Survey satellite, known simply as TESS, had been scanning the cosmos for 2 years by the time this particular signal caught attention. Launched with the mission to find Earth-like worlds orbiting nearby stars, TESS watches for the telltale dimming that occurs when a planet crosses in front of its host star. It's painstaking work, requiring the satellite to monitor hundreds of thousands of stars simultaneously, looking for patterns that repeat with clockwork precision. The star in question appeared unremarkable in the initial surveys. Catalogued as 8 Ursae Minoris, it sits 530 light-years away in the constellation Ursa Minor, glowing with the dim orange light of a dying giant. To most observers, it would seem like countless other aging stars scattered throughout the galaxy. But TESS detected something extraordinary. Every 93 days, the star's brightness dipped by a fraction of a percent, then returned to normal. The pattern repeated with mechanical regularity, the signature of an orbiting planet. At first, the Discovery team treated it as routine. Planets around aging stars weren't unusual, and the 93-day orbital period suggested a world roughly half the distance from Earth to the Sunday. Standard analysis began immediately. Mass estimates, orbital calculations, atmospheric modelling, all straightforward procedures for cataloguing another distant world. Then came the first red flag. Dr. Mark Hahn, a postdoctoral researcher at the University of Hawaii, was running the stellar classification algorithms when something didn't add up. The host star's spectral data indicated it was a red giant, a massive star in the final stages of its life. But red giants expand dramatically as they age, growing to hundreds of times their original size. If 8 Ursae Minoris had reached this phase, it should have expanded far beyond the orbit of any closely circling planet. Hahn ran the calculations again. According to stellar evolution models, the star should have swollen to roughly 7/10 of an astronomical unit, the distance from Earth to the Sunday. But the planet appeared to orbit at just 5/10 of that distance. In other words, the star should have engulfed and vaporized the planet long ago. The initial reaction among the research team was dismissal. Clearly, there had been an error in the data processing. Perhaps the stellar classification was wrong, or the orbital distance had been miscalculated. Such mistakes weren't uncommon in the early stages of planet hunting, when subtle signals could be misinterpreted by automated systems. But as the team dug deeper, the anomaly only became more pronounced. Asteroseismology, the study of stellar oscillations, provided a precise fingerprint of the star's internal structure and evolutionary state. The oscillation patterns were unmistakable. 8 Ursae Minoris was indeed a red giant in the helium-burning phase, long past the period when it should have expanded to its maximum size. The planet, meanwhile, showed all the characteristics of a stable, long-term orbit. No signs of rapid orbital decay, no evidence of recent gravitational disruption. It appeared to have been circling its host star peacefully for eons, as if completely unaware that it should have been destroyed billions of years ago. Word of the discovery began to spread through the astronomical community in hushed tones. Here was a world that existed in direct violation of everything scientists understood about stellar evolution and planetary dynamics. It was as if someone had discovered a house sitting peacefully in the middle of a forest fire, completely untouched by the flames. The implications were staggering. If 8 Ursae Minoris b could survive where it should have perished, what did that say about the thousands of other planetary systems being discovered around aging stars? How many other impossible worlds might be hiding in the data, dismissed as errors because they contradicted established theory? The discovery team knew they were looking at something unprecedented, but they also knew that extraordinary claims require extraordinary evidence. Every aspect of the detection would need to be verified, every possible source of error eliminated. The astronomical community had a long history of embarrassing false alarms, and no one wanted to stake their reputation on a planet that couldn't exist. Over the following months, additional observations confirmed the impossible. Ground-based telescopes tracked the planet's gravitational influence on its star, measuring the tiny wobble caused by their mutual orbit. Space-based instruments monitored additional transits, refining the orbital parameters to unprecedented precision. Every measurement confirmed the same impossible conclusion. The planet was real. It was exactly where the data said it was. And according to every model of stellar evolution, it should have been reduced to vapor and stellar wind long before TESS ever turned its cameras toward that distant corner of the sky. As news of the discovery leaked to the broader scientific community, reactions ranged from fascination to skepticism to outright disbelief. Some researchers immediately began developing new theories to explain the impossible survival. Others questioned whether the stellar classification might be wrong, despite the overwhelming spectroscopic evidence. A few suggested that the planet might be a recent arrival, somehow captured or formed after the star's dangerous expansion phase. But deep down, most astronomers recognized they were confronting something that challenged the foundations of planetary science. Here was a world that existed where no world should exist, orbiting peacefully around a star that should have killed it. And if one impossible planet could survive the unsurvivable, how many others might be waiting to be discovered? The planet that would eventually be named Hala had announced its presence to the universe. Now came the far more difficult task of explaining how it got there and what its existence meant for everything scientists thought they knew about the life and death of planetary systems. In the sterile halls of the Space Telescope Science Institute, researchers stared at their computer screens and contemplated the impossible. Somewhere in the constellation Ursa Minor, a world that shouldn't exist continued its eternal dance around a dying star, defying the very laws that should have destroyed it eons ago. Chapter 2: A Star in its Death Throes. To understand why Hala's existence defies cosmic law, you must first understand the violent transformation that occurs when a star begins to die. 8 Ursae Minoris, is not the steady, life-giving sun that Earth knows. It is a stellar giant in the final act of a 10-billion-year drama, swollen to dimensions that would horrify any planet unlucky enough to orbit nearby. Picture our own sun, that familiar golden disk that rises each morning, warm and constant. Now imagine it growing larger, first doubling in size, then 10 times larger, then 100 times its original diameter, the surface cooling from brilliant yellow to deep orange, then to the dull red glow of dying embers. This is the fate that awaits all stars like our sun, and it is the transformation that 8 Ursae Minoris completed billions of years ago. The physics of stellar death begins deep within the star's core, where nuclear fusion has burned steadily for most of the star's lifetime. For billions of years, hydrogen atoms have been crushed together under immense pressure and temperature, fusing into helium and releasing the energy that keeps the star shining. But hydrogen is not infinite. Eventually, even in a star's vast core, the fuel begins to run low. When the hydrogen supply dwindles, the delicate balance that has sustained the star for eons begins to collapse. Gravity, which has always pulled inward, starts to win its ancient battle against the outward pressure of nuclear fusion. The core contracts, becoming denser and hotter. But this compression triggers a strange and violent response. The star's outer layers, no longer supported by the steady pressure from below, begin to expand outward into space. This expansion is not gradual. In cosmic terms, it happens with startling speed. Over just a few million years, a star like 8 Ursae Minoris can grow from roughly the size of our sun to a bloated giant, spanning hundreds of times its original diameter. If our sun underwent this transformation, its surface would extend past the orbit of Mars, consuming Mercury, Venus, and Earth in a blazing embrace. The expanding star becomes what astronomers call a red giant, though the name hardly captures the awesome scale of the transformation. The surface temperature drops as the star's energy spreads across its vastly increased area, giving it that characteristic ruddy glow. But make no mistake about the gentleness of that soft red light. The star's luminosity, its total energy output, actually increases during this phase. What appears as a gentle ember from across interstellar space is actually a cosmic furnace of unimaginable ferocity. Any planet caught within the expanding envelope faces certain destruction. The stellar material, though thin by earthly standards, is still dense enough to create enormous friction against an orbiting world. The planet's orbit begins to decay as it ploughs through the star's outer atmosphere. Tidal forces stretch and distort the world's shape. Most catastrophically, the intense heat and radiation strip away the planet's atmosphere and begin to vaporize its surface. The end comes swiftly. Within a few thousand years, sometimes much less, the planet spirals inward toward the star's core, its material torn apart and scattered into the expanding stellar wind. Nothing remains but traces of heavy elements mixed into the star's outer layers, the only evidence that a world once existed in that orbital space. This is the fate that should have befallen Hala billions of years ago. 8 Ursae Minoris expanded to roughly 7/10 of an astronomical unit from its centre. Hala orbits at just half that distance. By every model of stellar evolution, the planet should have been deep within the star's envelope when it reached maximum size, subjected to temperatures of thousands of degrees and friction that would have torn it apart within centuries. But asteroseismology, the study of stellar oscillations, tells us something remarkable about 8 Ursae Minoris. Just as seismologists study earthquakes to understand Earth's interior structure, astronomers can analyze the subtle vibrations of a star's surface to map its internal composition and evolutionary state. These stellar heartbeats, detected by instruments sensitive enough to measure brightness changes of less than 1 part per million, reveal the star's deepest secrets. The oscillation patterns of 8 Ursae Minoris are unmistakable. They match the signatures of a red giant in the helium burning phase, long past its period of maximum expansion. The star has already undergone its dramatic swelling and has settled into the later stages of its evolution. The core now burns helium into carbon and oxygen, while the outer layers have contracted somewhat from their peak size. This is not a star still approaching its red giant phase. This is a star that completed its expansion eons ago. The implications are staggering. The stellar physics is well understood and thoroughly tested. Red giants expand predictably, following patterns observed in thousands of similar stars throughout the galaxy. There is no known mechanism by which a planet at Halle's distance could survive the expansion phase. The temperatures alone, reaching several thousand degrees, would vaporize rock and metal. The orbital friction would cause the planet to spiral inward to its destruction within geological timescales that are brief even by cosmic standards. Yet there Halle orbits, completing its 93-day journey around a star that should have consumed it. The planet shows no signs of recent formation, no evidence of unusual composition that might explain enhanced survival. Its orbit is stable and nearly circular, suggesting it has been in its current configuration for millions or billions of years. The puzzle deepens when astronomers consider the star's mass. 8 Ursae Minoris contains roughly 1.7 times the mass of our Sun, making it more massive than the average star. More massive stars actually expand even further during their red giant phase, making planetary survival at close distances even more unlikely. The physics works against Halle's existence in every possible way. Some researchers have suggested that perhaps the stellar models are incorrect, that 8 Ursae Minoris never expanded as far as predicted, but the astroseismic data leaves no room for doubt. The star's internal structure, its surface oscillations, and its spectral characteristics all confirm that it has undergone the full red giant transformation. There is no escaping the conclusion that this star once swelled to dimensions that should have obliterated any nearby planet. As astronomers continue to study this impossible system, they confront a fundamental challenge to their understanding of stellar evolution and planetary dynamics. The laws of physics that govern the life and death of stars are among the most thoroughly tested and reliable in all of science. Yet here stands a world that exists in defiance of those laws, orbiting peacefully around a star that should have destroyed it eons ago. In the soft red glow of 8 Ursae Minoris, something extraordinary has occurred. Whether it was a cosmic accident, an unknown physical process, or something even more remarkable, Halle's survival has rewritten the rules of what is possible in the violent universe of dying stars. Chapter 3: The Planet That Lived. 530 light-years from Earth, in the dim constellation of Ursa Minor, a world defies death with every orbit it completes. Halle, as astronomers have named it, is no ordinary planet. It is a gas giant weighing 1.3 times the mass of Jupiter, wrapped in clouds of hydrogen and helium that have somehow survived the cosmic furnace that should have stripped them away eons ago. Every 93 days and 4 hours, Halle completes one full journey around its dying star. The precision is remarkable, a celestial clockwork that has continued for millions or perhaps billions of years. At its closest approach, the planet skims just half an astronomical unit from 8 Ursae Minoris, roughly the distance that would place it between the Sun and the asteroid belt in our own solar system. But unlike the cold rocks of our asteroid belt, Hala moves through space heated by the angry glow of a red giant star. The orbit itself tells a story of impossible stability. When astronomers first calculated Hala's path, they expected to find signs of decay, evidence that the planet was spiraling inward toward its eventual destruction. Planets orbiting this close to evolved stars typically show orbital degradation, their paths slowly tightening as tidal forces and atmospheric drag take their toll. But Hala's orbit remains stubbornly circular, with an eccentricity so low it suggests the planet has been in gravitational equilibrium for vast periods of time. This circular orbit is perhaps the most puzzling aspect of Hala's existence. If the planet had somehow survived its star's red giant expansion through some unknown mechanism, astronomers would expect to see evidence of that trauma written in its orbital parameters. A highly elliptical path, perhaps, stretched and distorted by gravitational chaos, or signs of recent capture, the irregular orbit of a world that had been flung through space before settling into its current position. Instead, Hala orbits with the serene regularity of a planet that has never known catastrophe. Its gravitational influence on 8 Ursae Minoris creates tiny wobbles in the star's position, wobbles so subtle they require months of precise measurement to detect. These wobbles follow the mathematical curves of a stable two-body system, with no hint of the gravitational chaos that should have accompanied the planet's brush with stellar death. The planet's mass presents its own set of mysteries. At one point, 3 Jupiter masses, Hala is substantial enough that it should have influenced its star's evolution in measurable ways. When massive planets orbit close to their stars, they can trigger enhanced stellar activity, create magnetic field interactions, and even affect the timing of stellar expansion phases. But 8 Ursae Minoris shows no signs of such planetary influence, suggesting either that the planet arrived recently or that it has somehow avoided the gravitational dance that typically develops between close-in giants and their host stars. Temperature models of Hala's surface paint a picture of a world caught between ice and fire. At its current distance from 8 Ursae Minoris, the planet receives roughly 4 times the radiation that Jupiter gets from our Sunday. This intense heating should create powerful atmospheric dynamics, with supersonic winds and temperature differences that could tear apart weaker atmospheric structures. Yet spectroscopic observations suggest Hala maintains a stable atmosphere, its hydrogen and helium envelope intact despite the stellar bombardment it endures. The planet's composition offers another puzzle for astronomers trying to understand its survival. Gas giants like Hala are predominantly made of the lightest elements in the universe, hydrogen and helium, that should be the first to boil away when exposed to intense stellar radiation. Rocky planets might survive close encounters with red giants, their heavy elements requiring much higher temperatures to vaporize. But a gas giant maintaining its atmospheric envelope this close to an evolved star challenges basic models of planetary atmospheric evolution. Some researchers have suggested that Hala might possess an unusually strong magnetic field, a planetary magnetosphere powerful enough to deflect the worst of its star's particle bombardment. Jupiter's magnetic field creates a protective bubble around that planet, shielding its moons from the radiation environment of the outer solar system. Perhaps Hala possesses a similar but even more powerful magnetic shield, one capable of protecting its atmosphere from the intense stellar wind of a red giant. But even the strongest magnetic field has limits. The temperatures that Hala experienced during 8 Ursae Minoris's red giant phase would have been measured in thousands of degrees, hot enough to ionize atmospheric gases and overwhelm any reasonable magnetic protection. No known mechanism could shield a planet's atmosphere from the direct immersion in stellar material that Hala should have experienced. The planet's orbital period of 93 days creates another layer of mystery. This timing places Hala in what astronomers call a resonant orbit, where the planet's gravitational influence on its star creates regular, repeating patterns. Such resonances typically develop over long periods of stable orbital evolution, requiring millions of years of gradual adjustment between planet and star. The presence of this resonance suggests that Hala has been in its current orbit for far longer than any survival scenario should allow. Transit observations from the Transiting Exoplanet Survey satellite reveal that Hala passes directly between Earth and 8 Ursae Minoris during each orbit, creating tiny eclipses that last for several hours. These transits provide astronomers with unprecedented detail about the planet's size, density, and atmospheric properties. The data confirms that Hala is indeed a gas giant, with characteristics similar to Jupiter, showing no signs of the atmospheric stripping or density changes that would be expected from a world that had survived close contact with stellar fire. Perhaps most remarkably, follow-up observations have detected what appears to be a faint ring system around Hala. Rings are among the most fragile structures in planetary systems, easily disrupted by gravitational perturbations or intense radiation. The fact that Hala may have retained its rings through whatever process allowed it to survive its star's expansion suggests an even more impossible level of cosmic stability. The planet's very existence has forced astronomers to reconsider fundamental assumptions about planetary system evolution. For decades, the fate of planets around dying stars seemed well understood. Close-in worlds would be consumed, while distant planets might survive to orbit the eventual white dwarf remnant. Hala represents a third category that shouldn't exist, a close-in survivor that has somehow threaded the needle between destruction and escape. As observations continue, each new detail about Hala only deepens the mystery. The planet appears utterly normal by every measure except for its impossible location. Its mass, composition, orbital characteristics, and atmospheric properties all fall within the expected ranges for gas giants. It is a perfectly ordinary planet in a perfectly impossible place. Somewhere in the constellation Ursa Minor, Hala continues its eternal dance around 8 Ursae Minoris. Each 93-day orbit a testament to cosmic possibilities that our best theories cannot explain. In the soft red glow of its dying star, this impossible world spins through space, carrying with it the secrets of how planets can survive the unsurvivable and emerge unscathed from stellar catastrophe. The planet that lived has rewritten the rules of cosmic survival, proving that sometimes the impossible is simply what we haven't yet learned to understand. Chapter 4. When Giants Collide. When faced with the impossible existence of Hala, astronomers turned to one of the most violent scenarios in the cosmic catalogue, the collision and merger of two stars. Perhaps, they reasoned, 8 Ursae Minoris had not always been alone. Perhaps it once shared its space with a stellar companion, and in the catastrophic drama of their merger, the normal rules of planetary destruction had been rewritten. The binary merger hypothesis emerged from a simple but profound question. What could possibly alter a star's evolution so dramatically that a close-in planet might survive? The answer lay in the complex physics of stellar companions and the chaos that ensues when two stars become one. Binary star systems are common throughout the galaxy, with roughly half of all stars existing in gravitationally bound pairs or groups. These cosmic couples often dance around each other for billions of years, their mutual gravity creating intricate orbital ballets that can persist for the entire lifetime of both stars. But sometimes, this celestial waltz ends in collision. According to the merger theory, 8 Ursae Minoris once had a companion star, perhaps slightly smaller in mass, orbiting at a distance that brought it dangerously close during the primary star's red giant expansion. As 8 Ursae Minoris began to swell in its death throes, its outer envelope reached toward its companion, and the two stars entered a phase of violent interaction that astronomers call a common envelope event. Picture the chaos of this cosmic catastrophe. The primary star, already swollen to hundreds of times its original size, engulfs its smaller companion in a shroud of hot gas and plasma. The companion star, suddenly immersed in the outer layers of its partner, experiences tremendous friction as it plows through the stellar material. This friction causes the companion's orbit to decay rapidly, spiraling inward toward the core of the primary star. But the companion does not go quietly. As it spirals through the primary's envelope, it deposits enormous amounts of orbital energy into the surrounding stellar material. This energy injection heats and accelerates the envelope, causing much of it to be blown away into space in a spectacular stellar wind. The process is violent beyond imagination, with temperatures reaching hundreds of thousands of degrees and mass loss rates that can strip away significant portions of both stars in just a few thousand years. Computer simulations of these merger events reveal the extraordinary complexity of the physics involved. Magnetohydrodynamic codes, running on supercomputers for weeks at a time, attempt to model the turbulent flow of stellar plasma as two massive objects spiral together. The calculations must account for gravity, magnetic fields, radiation pressure, and the complex thermodynamics of partially ionized gas at extreme temperatures and densities. These simulations suggest that merger events can fundamentally alter the evolutionary path of the surviving star. The mass loss during the common envelope phase can reduce the star's total mass significantly, changing the timescales for nuclear burning and the eventual size of the red giant phase. More dramatically, the spiral-in process can deposit helium-rich material into the core of the primary star, potentially triggering new phases of nuclear fusion that would not occur in a single star's normal evolution. The most intriguing possibility is that the merger process could cause the primary star to contract rather than continue expanding. If the companion star deposits enough energy and angular momentum into the primary's core, it might reignite nuclear burning in a way that stabilizes the star at a smaller size. Instead of continuing to expand to its maximum red giant radius, the star might halt its growth or even contract slightly, potentially sparing any planets that orbit beyond the final envelope boundary. For Hala, this scenario offers a narrow window of survival. If 8 Ursae Minoris once had a companion that merged with it at just the right time in its evolution, the planet might have escaped destruction by the smallest of margins. The merger would need to occur after the star had expanded enough to threaten the planet, but before it reached full red giant size. The timing would have to be exquisitely precise. a cosmic coincidence of extraordinary rarity. The theory also explains some of the unusual chemical signatures observed in 8 Ursae Minoris. Stellar mergers often leave distinctive fingerprints in the surviving star's spectrum, particularly elevated levels of lithium and other light elements that are typically destroyed in stellar interiors. Observations of 8 Ursae Minoris do indeed show unusually high lithium abundance, roughly 10 times what would be expected for a normal red giant of its age and mass. This lithium enhancement provides tantalizing support for the merger hypothesis. During the violent mixing that occurs when two stars collide, material from the stellar envelopes can be dredged up and preserved in the outer layers of the surviving star. Lithium, which is easily destroyed by the high temperatures in stellar cores, can survive in the cooler envelope material and provide a chemical fossil of the merger event. The merger scenario also accounts for the apparent youth of 8 Ursae Minoris. If the star underwent a dramatic restructuring during the collision, its surface properties might reflect the time since the merger rather than its true age since formation. The mixing of stellar material during the event could reset some of the chemical clocks that astronomers use to determine stellar ages, making the star appear younger than it actually is. But the binary merger hypothesis requires a remarkable series of coincidences to work. The companion star would need to be the right mass to trigger the correct evolutionary response. The merger would need to occur at precisely the right phase of the primary star's evolution. The energy deposition would need to be sufficient to halt expansion, but not so violent as to disrupt the planet's orbit entirely. And the whole event would need to preserve Hala's nearly circular orbit despite the gravitational chaos of a stellar collision. Computer simulations struggle to reproduce such a perfect storm of circumstances. Most merger models either fail to halt the primary star's expansion sufficiently or create such violent conditions that any nearby planets would be ejected from the system entirely. The few scenarios that do preserve close-in planets typically result in highly elliptical orbits, very different from Hala's nearly circular path. The merger theory represents humanity's first serious attempt to explain the impossible. It invokes one of the most dramatic events in stellar evolution to account for Hala's survival, painting a picture of cosmic violence that's somehow preserved rather than destroyed. The idea that planetary systems could survive the collision of their parent stars speaks to the resilience of gravitational bonds and the unexpected outcomes that can emerge from cosmic catastrophe. Yet, even as astronomers refined the merger hypothesis, new observations were already challenging its foundations. The very coincidences that made the theory attractive also made it statistically unlikely. And hidden in the spectrum of 8 Ursae Minoris were clues that would soon cast doubt on whether a merger had occurred at all. In the vast darkness between the stars, stellar collisions write their stories in light and chemistry, in the subtle signatures that persist long after the violence has ended. But sometimes, even the most dramatic explanations fail to account for the full mystery of worlds that exist where they should not. Chapter 5: Secrets in Starlight. Light carries secrets across the cosmos, and nowhere is this more true than in the faint glow of 8 Ursae Minoris. Every photon that escapes the star's surface has been forged in nuclear fires and filtered through layers of stellar atmosphere, emerging with a chemical fingerprint that tells the story of the star's past. For astronomers seeking to understand Hala's impossible survival, this starlight would become both key evidence and devastating contradiction. The science of reading stellar history begins with spectroscopy, the art of splitting starlight into its component colours. When astronomers spread the light of 8 Ursae Minoris across a spectrum, they reveal thousands of dark absorption lines, each one marking where a specific element has absorbed photons of particular energies. These lines are as unique as fingerprints, allowing scientists to identify not just what elements exist in the star's atmosphere, but in what quantities and under what conditions. In the late 2010s, a team led by Dr. Huiling Chen at Peking University undertook the most comprehensive spectroscopic analysis of 8 Ursae Minoris ever attempted. Using the 1.93-metre telescope at the Haute-Provence Observatory in France, they captured high-resolution spectra that revealed the star's chemical composition in unprecedented detail. What they found would shatter the carefully constructed merger hypothesis and plunge Halle's existence back into mystery. The European Space Agency's Gaia spacecraft had already provided crucial supporting data. Launched in 2013, Gaia's mission was to map the positions and motions of more than 1 billion stars with extraordinary precision. For 8 Ursae Minoris, Gaia measured not just its location, but its proper motion across the sky, the tiny drift that reveals how the star moves through space relative to its galactic neighbours. This motion, combined with the star's radial velocity measured from Doppler shifts in its spectrum, painted a three-dimensional picture of 8 Ursae Minoris' journey through the galaxy. The data revealed that the star follows an orbit typical of younger stellar populations, moving in patterns consistent with formation in the galactic disk rather than the older stellar halo. This kinematic evidence suggested the star might be younger than the merger theory required, but it was the detailed spectroscopic analysis that delivered the decisive blow. Chen's team employed 3 independent methods to determine the star's age, each based on different physical principles and observable properties. The first approach used stellar isochrones, theoretical tracks that describe how stars of different masses evolve over time. By comparing 8 Ursae Minoris' temperature, luminosity, and surface gravity to these evolutionary models, the team could estimate when the star first began nuclear fusion. The second method relied on galactic chemical evolution, the gradual enrichment of heavy elements as generations of stars live, die, and seed space with the products of nuclear fusion. Stars that formed early in galactic history show lower abundances of elements heavier than hydrogen and helium, while younger stars inherit the enriched material from their stellar ancestors. The chemical fingerprint of 8 Ursae Minoris suggested formation during a relatively recent epoch of galactic evolution. The third approach used stellar kinematics, analysing the star's motion through the galaxy to determine its membership in different stellar populations. Young stars typically follow circular orbits in the galactic disk, while older stars show more eccentric paths that carry them high above and below the galactic plane. The orbital characteristics of 8 Ursae Minoris placed it firmly among the younger stellar population. All 3 methods converged on a shocking conclusion. 8 Ursae Minoris was only 1.9 to 3.5 billion years old. This was far younger than the 9 billion years that the merger hypothesis required to work. If the star had formed so recently, there simply hadn't been enough time for it to evolve through a complete stellar life cycle, acquire a companion star, undergo a merger, and settle into its current state. The implications rippled through the astronomical community like shockwaves. The merger theory, carefully constructed to explain Halle's survival, crumbled in the face of this new evidence. The star was too young to have undergone the complex evolutionary history that the hypothesis demanded. Something else entirely must account for the planet's impossible existence. Chen's team also made a crucial discovery about the star's mass. Previous estimates had placed 8 Ursae Minoris at roughly 1.5 solar masses, but the new analysis suggested it was actually 1.7 times as massive as our Sunday. This 13% increase might seem modest, but it carried profound implications for the planet's survival prospects. More massive stars expand even further during their red giant phase, making planetary survival at close distances even more unlikely. But the increased mass also meant that Hala's orbit, while still impossibly close, might be just barely outside the maximum extent of the star's expansion. The planet could be balanced on the very knife's edge between destruction and survival, saved by margins measured in millions of kilometers. The stellar oscillation data from TESS added another layer of complexity to the mystery. Asteroseismology, the study of stellar vibrations, had confirmed that 8 Ursae Minoris was indeed a red giant in the helium-burning phase. The star's surface pulsed with the characteristic rhythm of a star that had already completed its initial expansion. There was no doubt that the dangerous phase of stellar evolution had already passed. These oscillations also revealed subtle details about the star's internal structure. The frequencies of stellar vibrations depend on the density and composition of different layers within the star, allowing astronomers to peer into its hidden interior. The data showed no signs of the disrupted structure that might be expected from a recent merger event. The star appeared to have evolved normally, without the complex mixing and energy deposition that would characterize a stellar collision. The chemical composition told a similar story. While 8 Ursae Minoris did show elevated lithium levels compared to typical red giants, the enhancement was not as dramatic as merger models predicted. The star's spectrum lacked other chemical signatures that should accompany violent stellar interactions, such as unusual ratios of carbon to nitrogen or evidence of processed material from stellar cores. As the evidence mounted, astronomers faced an uncomfortable truth. Their best explanation for Hala's survival was wrong. The merger hypothesis, with all its dramatic violence and cosmic coincidences, could not account for a star too young to have undergone such a complex evolutionary history. The planet that shouldn't exist had defeated even the most exotic theoretical attempts to explain its presence. The starlight of 8 Ursae Minoris had spoken, and its message was clear. Whatever allowed Hala to survive the unsurvivable, it was not the collision and merger of two stars. The mystery was deeper than anyone had imagined, hidden in processes that science had yet to discover or understand. In the gentle glow of that distant red giant, photons continued their journey across space, carrying with them the chemical secrets of a star that had somehow preserved an impossible world. Each spectrum revealed new details, new constraints on what might have happened in that remote corner of the galaxy. But for all the precision of modern astronomical instruments, for all the sophistication of stellar evolution theory, the fundamental question remained unanswered. How does a planet survive when no planet should survive? The light of 8 Ursae Minoris had eliminated one possibility, but the cosmos held countless others, waiting to be discovered in the endless depths of space and time. Chapter 6: The Age Problem. In the quiet halls of Peking University, Dr. Huiling Chen stared at computer screens filled with spectroscopic data, watching as months of careful analysis converged on a conclusion that would overturn everything astronomers thought they knew about Hala's survival. The numbers were unforgiving, consistent across every method of measurement, pointing to a truth that made the impossible planet even more impossible. 8 Ursae Minoris was young, impossibly devastatingly young. The first hint had come from the stellar isochrone analysis, where Chen's team compared the star's observed properties against theoretical models of stellar evolution. Isochrones are like cosmic family trees, showing how stars of different masses age over billions of years. By plotting a star's temperature, brightness, and surface gravity on these evolutionary tracks, astronomers can read its age like rings in an ancient tree. For 8 Ursae Minoris, the isochrone analysis yielded an age of 1.9 billion years. This was not the ancient 9-billion-year-old star that the merger hypothesis required. This was a star that had formed when the universe was already 3/4 of its current age, a relatively recent arrival in cosmic terms. The second method, chemical age dating, told the same troubling story. Stars are time capsules, preserving in their atmospheres the chemical composition of the galactic region where they formed. The early universe contained almost nothing but hydrogen and helium, but billions of years of stellar death and supernova explosions have gradually enriched the galaxy with heavier elements. By measuring the abundance of these metals in a star's spectrum, astronomers can determine when it formed. 8 Ursae Minoris showed the chemical signature of a star born from relatively enriched material, consistent with formation 3.3 billion years ago. Once again, far too recent for the complex evolutionary history that the merger theory demanded. The third approach, kinematic age determination, examined how the star moved through the galaxy. Young stars typically follow smooth circular orbits in the galactic disk, while older stars have had time to be gravitationally scattered into more eccentric paths that carry them far from their birthplaces. The motion of 8 Ursae Minoris placed it squarely among the younger stellar population, with kinematics suggesting an age of 3.5 billion years. 3 independent methods, 3 consistent results, all pointing to the same impossible conclusion. 8 Ursae Minoris was between 1.9 and 3.5 billion years old, making it younger than Earth itself. The star that hosted an impossible planet was itself impossibly young to have undergone the dramatic evolutionary history that might explain that planet's survival. The implications struck the astronomical community like a physical blow. The binary merger hypothesis, carefully constructed to account for Haller's existence, required a star old enough to have lived through multiple phases of evolution. First, the primary star would need to age normally for several billion years. Then, it would require time to acquire a binary companion, either through capture or shared formation. The 2 stars would need to evolve together until the primary began its red giant expansion. Only then could the merger event occur that might save a close-in planet. This entire sequence demanded at least 9 billion years, probably more. But 8 Ursae Minoris had existed for less than 4 billion years, barely enough time to evolve into a red giant at all, let alone undergo the complex stellar interactions that the merger theory required. Chen's team double-checked their calculations, ran alternative models, and considered every possible source of error. Could stellar mergers somehow reset the chemical clocks they used for age determination? Could the mixing of stellar material during a collision create false signatures of youth? The answer, in every case, was no. The age estimates were robust, grounded in well-understood physics, and confirmed by multiple independent lines of evidence. The merger hypothesis lay in ruins. The dramatic scenario of stellar collision and planetary salvation, so carefully constructed to explain the unexplainable, could not account for a star too young to have lived such a complex history. Astronomers found themselves back at the beginning, confronting an impossible planet with no viable explanation for its existence. But the age problem created new mysteries, even as it solved old ones. If 8 Ursae Minoris was only a few billion years old, how had it already evolved through its entire red giant phase? Stars of its mass should take longer to exhaust their nuclear fuel and begin the expansion that threatens nearby planets. The youth of the star made its current evolutionary state almost as puzzling as the planet it hosted. Some researchers began to wonder if the star's evolution had been artificially accelerated. Could some unknown process have sped up nuclear burning, causing the star to age faster than normal stellar evolution models predicted? Such acceleration would require exotic physics, mechanisms that no known astrophysical process could provide. Others suggested that 8 Ursae Minoris might not be a normal single star at all. Perhaps it was the product of an early merger between two smaller stars, creating a more massive object that evolved faster than either component would have alone. But this idea faced its own problems. Early mergers typically leave distinctive signatures in stellar rotation and chemical composition, signatures that were not clearly present in 8 Ursae Minoris. The age determination also called into question fundamental assumptions about stellar evolution. If a star could reach red giant status in just a few billion years while hosting a surviving close-in planet, then perhaps the timescales and physical processes involved were not as well understood as astronomers had believed. The precision of modern stellar evolution models, tested against thousands of observed stars, suddenly seemed less certain when confronted with this single impossible example. For Haller itself, the age problem created a paradox within a paradox. Not only did the planet exist where it shouldn't, but it orbited a star that seemed too young to have threatened it in the first place. If 8 Ursae Minoris had only recently become a red giant, perhaps Haller had simply never faced the extinction event that theory predicted. But this explanation failed to account for the astroseismic evidence showing that the star had already completed its expansion phase and moved into helium burning. The precision of the age measurements also ruled out simple observational errors. Chen's team had used high-resolution spectroscopy, Gaia spacecraft astrometry, and multiple theoretical frameworks. The convergence of independent methods on similar age estimates gave confidence that the measurements were correct, even if their implications were difficult to accept. As news of the age problem spread through the research community, other astronomers began re-examining their own assumptions about stellar evolution and planetary survival. If one impossible planet could exist around one impossibly young evolved star, might there be others? The discovery triggered searches for similar systems, worlds that might have survived, where no world should survive around stars too young to have threatened them. The age problem also highlighted the limitations of theoretical models when confronted with unusual observations. Stellar evolution theory, planetary dynamics, and binary star evolution were all mature fields with decades of observational confirmation. Yet, when combined in the unique circumstances of the 8 Ursae Minoris system, these well-tested theories failed to provide a coherent explanation. In the sterile fluorescent light of university computer labs, astronomers continued to wrestle with data that refused to fit existing frameworks. Each new measurement of 8 Ursae Minoris seemed to deepen rather than resolve the mystery. The star was too young, the planet too close, the entire system too stable for any known physical process to explain. Somewhere in the constellation Ursa Minor, Haller continued its 93-day orbit around a star that challenged the very foundations of astronomical understanding. The impossible planet had defeated not just the normal rules of planetary survival, but the exotic scenarios invented to explain its existence. In the soft red glow of 8 Ursae Minoris, a world that shouldn't exist orbited a star too young to have created the conditions that should have destroyed it. The age problem had eliminated the most promising explanation for cosmic impossibility, leaving astronomers to confront a universe stranger than their best theories could accommodate. Chapter 7: Gravitational Mysteries. With the merger hypothesis crumbling under the weight of stellar age measurements, astronomers turned their attention to the one piece of new data that offered a glimmer of hope: the revised mass of 8 Ursae Minoris. Sometimes, salvation comes not from dramatic cosmic violence, but from the subtle recalculation of fundamental properties that shift the boundary between destruction and survival by the narrowest of margins. Chen's team had determined that 8 Ursae Minoris contained 1.7 solar masses, roughly 13% more massive than previous estimates had suggested. In the context of planetary survival around dying stars, this seemingly modest revision carried profound implications. More massive stars burn brighter and evolve faster, but they also possess stronger gravitational fields that can hold their outer layers more tightly during the red giant expansion phase. The physics of stellar expansion involves a delicate balance between gravitational contraction and radiation pressure. As a star exhausts its core hydrogen and begins burning helium, the outer layers must respond to changing energy output and internal structure. A more massive star experiences stronger gravitational forces throughout this process, potentially limiting how far the stellar envelope can expand before gravity pulls it back. For Haller, orbiting at just half an astronomical unit from its host star, even small differences in maximum stellar radius could mean the difference between incineration and survival. If the original mass estimates had been correct, 8 Ursae Minoris would have expanded to roughly 7/10 of an astronomical unit during its red giant phase, easily engulfing the planet's orbit. But with the revised mass of 1.7 solar masses, theoretical models suggested the expansion might have reached only 6.8 or 6.9 of an astronomical unit. These numbers dance on the knife's edge of possibility. Haller's orbit at 0.5 astronomical units would still place it perilously close to the stellar envelope at maximum expansion. The planet would have skimmed the outermost layers of its star's atmosphere, experiencing temperatures of thousands of degrees and atmospheric friction that should have torn it apart within centuries or millennia. Yet the gravitational dynamics of such close encounters are more complex than simple geometric considerations might suggest. As Haller ploughed through the tenuous outer layers of its expanding star, it would have transferred orbital energy to the stellar material through tidal interactions and atmospheric drag. This energy transfer would have accelerated the stellar wind, helping to blow away the very envelope that threatened the planet's existence. Computer simulations of planet envelope interactions reveal the extraordinary complexity of the physics involved. The planet's gravity would create spiral density waves in the surrounding stellar material, patterns of compression and rarefaction that could either enhance or reduce the local gas density. Magnetic field interactions between the planet and the ionized stellar plasma could generate additional heating and mass loss. The planet itself might develop a protective magnetosphere, deflecting some of the stellar wind and creating a partial vacuum in its wake. These simulations also suggest that planetary survival depends critically on the rate of stellar expansion. If 8 Ursae Minoris swelled too quickly, Hala would have been overwhelmed before it could clear enough stellar material to create a survivable environment. If the expansion proceeded too slowly, the planet would have spiraled inward to destruction before the stellar envelope receded. The timing would need to be exquisitely precise, a cosmic choreography of expansion and orbital decay that preserved the planet by margins measured in thousands of kilometers and hundreds of years. The revised mass estimates also affect the internal structure and evolution of 8 Ursae Minoris in ways that could influence Hala's survival prospects. More massive stars have higher core temperatures and pressures, leading to faster nuclear burning rates and shorter lifetimes on the main sequence. But they also develop more complex internal structure during their red giant phases, with multiple burning shells and convective zones that can dramatically alter the star's surface properties. In particular, the helium flash phase that marks the transition from hydrogen shell burning to helium core burning can cause rapid changes in stellar radius and luminosity. For a star of 1.7 solar masses, this transition might occur more violently than in lower mass stars, potentially creating conditions where the stellar envelope is partially ejected rather than smoothly expanded. Such mass loss events could reduce the peak radius reached during the red giant phase, providing additional margin for planetary survival. The gravitational effects extend beyond simple radius calculations to encompass the entire orbital dynamics of the planet-star system. As 8 Ursae Minoris lost mass during its red giant phase through stellar winds and envelope ejection, Hala's orbit would have expanded slightly due to the reduced gravitational attraction. This orbital evolution could have carried the planet outward just as the stellar envelope expanded inward, creating a narrow window where destruction was avoided by the interplay of stellar mass loss and orbital mechanics. Tidal forces also play a crucial role in determining whether a close-in planet can survive stellar expansion. The gravitational field of a red giant is not uniform across a planet's orbit, creating differential forces that can elongate the planet and pump energy into its rotation and internal structure. For gas giants like Hala, these tidal effects can cause the planet's atmosphere to puff up, potentially making it more vulnerable to stellar winds and radiation. But tidal heating can also work in the planet's favour by driving atmospheric circulation patterns that help distribute heat and create more uniform temperature conditions. Strong tidal forces might even trigger enhanced magnetic field generation within the planet's core, providing better protection against stellar particle bombardment. The balance between destructive and protective tidal effects depends on subtle details of planetary structure and composition that remain largely unknown for distant worlds like Hala. The 13% mass revision also influences the chemical evolution of 8 Ursae Minoris during its red giant phase. More massive stars dredge up different mixtures of nuclear-processed material from their interiors, potentially creating surface compositions that affect stellar wind properties and mass loss rates. The enhanced lithium abundance observed in 8 Ursae Minoris might reflect these mass-dependent mixing processes, rather than the dramatic stellar mergers that the previous hypothesis required. Perhaps most intriguingly, the revised mass places 8 Ursae Minoris near a critical threshold in stellar evolution. Stars just above 1.7 solar masses can experience fundamentally different evolutionary pathways than slightly less massive stars, including the possibility of blue loop evolution, where the star briefly returns to higher surface temperatures after its initial red giant phase. Such evolutionary peculiarities could create unexpected opportunities for planetary survival that are not captured in standard stellar evolution models. Yet even with the most optimistic interpretation of the mass revision, Hala's survival remains statistically improbable. The margins are simply too narrow, the coincidences too numerous, for gravitational dynamics alone to provide a complete explanation. The planet would need to thread the needle of stellar expansion with extraordinary precision, avoiding destruction by distances that represent less than 1% of its orbital radius. The gravitational mysteries surrounding Hala's survival illustrate the profound sensitivity of planetary fate to seemingly minor changes in stellar properties. A difference of just 0.2 solar masses, barely detectable with earlier observational techniques, shifts the boundary between certain destruction and possible survival. In the vast cosmos, where stellar masses span orders of magnitude, such precision seems almost impossibly fine-tuned. As astronomers continue to refine their measurements of 8 Ursae Minoris, each new decimal place in the mass determination carries profound implications for understanding Hala's existence. The gravitational forces that should have destroyed the planet may have been just barely insufficient to complete the task, leaving behind a world balanced on the edge between existence and oblivion. In the gentle pull of gravity across half an astronomical unit of space, Hala continues its eternal dance around 8 Ursae Minoris, held in an orbit that represents one of the most improbable outcomes in the known galaxy. Whether this improbability reflects extraordinary luck, unknown physics, or processes yet to be discovered, remains the central mystery of the planet that shouldn't exist. Chapter 8. Born from Chaos. What if Hala was never meant to survive the death of 8 Ursae Minoris? What if, instead, it was born from that death, forged in the aftermath of stellar destruction, a second-generation world rising from the ruins of its system? As traditional theories collapsed under the weight of observation, astronomers began to consider a radical new idea. Perhaps Hala is not a relic of the past, but a cosmic newborn, created in the chaos that followed a stellar catastrophe. This hypothesis, often referred to as planetary resurrection, challenges the core assumptions of how planets form and persist. In standard models, planets emerge early, coalescing from disks of gas and dust around young stars, and then endure for billions of years until their stars reach the end of their lives. But what if that process can begin again, not once, but multiple times within a single stellar system, triggered by cosmic violence? The inspiration for this idea comes from real observations across the galaxy. When two stars collide and merge, the event is spectacular, ejecting vast amounts of enriched material into surrounding space. This stellar debris can settle into rotating disks of gas and dust, forming conditions surprisingly similar to the environments that give birth to the original planets. Under the right circumstances, new planets can form from old stars. Applied to 8 Ursae Minoris, the theory unfolds like this. Billions of years ago, it may have existed in a binary system. Over time, gravitational forces brought the two stars closer together until they finally merged in a violent collision. This event, would have ejected a massive disk of stellar material, hot, dense, and rich in heavy elements. As the disk cooled, gravitational instabilities could have triggered the birth of new planets, including Hala. Planets formed in this way would be chemically exotic. Unlike planets born in the relatively pristine environment of a young stellar disk, second-generation worlds would be rich in heavy elements and unusual isotopes, byproducts of the intense nuclear fusion that once occurred deep within stars. Such worlds might have thicker atmospheres, stronger magnetic fields, or internal heat sources that make them more resilient to harsh stellar conditions. The timeline supports the idea. While planetary formation from merger debris would still require 10 to 100 million years, that leaves billions of years for the resulting planets to orbit peacefully while their host star, now a merged object, ages and eventually expands into a red giant. The age of 8 Ursae Minoris, estimated at 3 to 4 billion years, might be just enough for this sequence of events to unfold. Clues in support of this idea come from the star itself. Spectroscopic studies have revealed that 8 Ursae Minoris has a higher than normal lithium abundance, a trait often linked to stellar mergers. Lithium, typically destroyed in stellar interiors, can be reintroduced to the surface during such events. While not definitive, this anomaly offers a potential fingerprint of a long-ago merger. Even more compelling are subtle anomalies in the star's surface composition. High-resolution spectroscopic measurements have identified certain rare isotopes that do not match the expected outputs of typical stellar evolution. These may have been forged in the unique nuclear reactions triggered by a merger, then mixed into the star's outer layers and preserved over eons. Hala's own orbit adds to the mystery. Second-generation planets, born in a smooth, dissipating disk of debris, would tend to settle into stable, nearly circular orbits, aligned with the disk's plane. Hala's orbit is remarkably circular and stable, an unusual trait for a planet that supposedly survived a star's death throes. If it formed after the chaos, not before, this orbit makes more sense. Simulations of stellar mergers have begun to shed light on how such planets might form. These computer models examine the dynamics of stellar collisions, the structure of resulting disks, and the possibility of accreting planetary cores from heavy element-rich material. While second-generation planets are difficult to form, they are not impossible. The key is in the balance. The merger must be violent enough to expel material, but not so energetic as to disperse it entirely. According to the models, only certain kinds of mergers create the conditions for planet formation. The disk must be dense enough to allow for gravitational collapse, but not so turbulent that accretion is prevented. The merged star must also remain stable for long enough, hundreds of millions of years, to allow planets to coalesce, cool, and settle into orbits. Perhaps most remarkably, second-generation planets may be better suited to survival than their first-generation counterparts. Their enriched chemistry and thick atmospheres could offer more resistance to radiation. Stronger magnetic fields might protect them from stellar winds during the red giant phase. If true, such planets would not only form in chaos, but thrive in it. This theory could also explain why Hala has not lost its atmosphere, despite orbiting a red giant that should have stripped it bare. If it formed from dense, high metallicity material, it may be more massive or compact than other gas giants, giving it a stronger gravitational grip on its gaseous envelope. Of course, the resurrection scenario is not without its challenges. Detecting a stellar merger that occurred billions of years ago is almost impossible. The chemical evidence, while suggestive, is not definitive. Other processes, like internal stellar mixing or contamination from interstellar dust, could potentially mimic the observed anomalies. Moreover, most models predict that high metallicity environments favor the formation of rocky planets, not gas giants. Forming a planet as large as Hala, a true gas giant, would likely require conditions that are rare and extreme, possibly making second-generation gas giants even more improbable than long-term survivors. The time constraint is also tight. In only a few billion years, the system must undergo a merger, form a debris disk, accrete a gas giant, and evolve into a red giant. It is a tall order, but not an impossible one. Ultimately, the resurrection hypothesis shifts the question from how did this planet survive to how could it have formed? It paints 8 Ursae Minoris not as a destroyer, but as a creator, a cosmic phoenix whose death birthed something entirely new. If proven true, this theory could revolutionize our understanding of planetary systems. It would suggest that stars have second chances, that planets can form more than once in the same place, and that destruction may be just the beginning of creation. In the red light of 8 Ursae Minoris, one question endures. Is Hala a ghost from the past, or a child of chaos? The answer may lie in the chemistry of stars, the mathematics of mergers, and the silent testimony of a planet that should not exist, but does. Chapter 9. Signals from the Impossible. In the cold silence of space, 200 miles above Earth's surface, the Transiting Exoplanet Survey satellite, known simply as TESS, orbits the planet with quiet determination. Its 4 wide-field cameras gaze steadily into the cosmos, capturing the faintest flickers of light. Designed not to seek the strange but the familiar, TESS was meant to find Earth-like worlds orbiting sun-like stars, planets that might support life. Yet, in its meticulous scan of the sky, this robotic sentinel has become our most powerful tool for discovering the impossible. The technique that revealed Hala's existence relies on one of astronomy's subtlest tricks, the transit method. When a planet crosses in front of its host star, it briefly dims the star's light. For gas giants, this reduction may be less than 1%. For rocky planets like Earth, the dimming can be as small as 1 part in 10,000. TESS must detect these minute signals against a backdrop of cosmic and instrumental noise. TESS does so with astonishing precision, measuring brightness variations as small as 20 parts per million, equivalent to detecting the light of a single candle flickering out in a stadium filled with spotlights. Its charge-coupled device cameras, each boasting over 16 million pixels, continuously monitor enormous swaths of the sky. Every 2 minutes, TESS records the brightness of hundreds of thousands of stars, generating a nearly continuous time-lapse of stellar activity across the heavens. In the case of 8 Ursae Minoris, TESS detected the unmistakable pattern of a planetary transit, an event that repeated with clockwork precision every 93 days and 4 hours. Each time, the star's light dimmed by approximately 0.8%, a subtle signal that recurred over and over. This pattern was the calling card of a planetary companion, Hala. But finding that signal was no small feat. Red giant stars like 8 Ursae Minoris are notoriously noisy. Their surfaces roil with convection, magnetic fields, and oscillations, complex brightness variations that can easily obscure or mimic planetary signals. Isolating a real transit requires intricate algorithms that can identify repeating patterns hidden within chaos. The TESS data pipeline begins with meticulous calibration. Thermal fluctuations, cosmic ray strikes, and detector drift must all be corrected before analysis can even begin. Then comes the removal of common mode noise, variations that affect many stars simultaneously, typically caused by spacecraft motion or temperature changes. Only then can individual stars be studied in detail. With 8 Ursae Minoris, additional care was needed. Red giants pulsate with multiple oscillation modes, which introduce irregularities in brightness and complicate transit detection. These pulsations, while scientifically valuable for studying the star's interior, act like static when hunting for a planetary signal. Yet, buried in that stellar noise was the consistent, symmetrical dip that signaled Halle's transit. The light curve, the graph of brightness over time, held more than just confirmation of a planet. Its depth revealed Halle's radius. Its duration gave clues to the planet's orbital speed and angle. The precise timing of each transit, measured across multiple years, revealed the planet's orbital period with astonishing accuracy. Even more nuanced features of the light curve told stories. Subtle curvatures at the beginning and end of the transit, known as ingress and egress, reflected limb darkening, a natural gradient in stellar brightness caused by temperature differences across the star's disk. These details further confirmed that the signal was not an artifact but a real, physical planet. However, to be certain, ground-based follow-up was essential. Using high-resolution spectrographs, astronomers measured the radial velocity of 8 Ursae Minoris, the tiny wobble induced by Halle's gravity as it tugs on its star. This wobble, measuring only a few meters per second, is like detecting a walking pace in a star hundreds of light years away. Such precision requires instruments operating at near cryogenic stability. Even temperature changes of a few thousandths of a degree can disrupt the data. Red giants make these measurements even more difficult. Their surface oscillations, which are much larger in magnitude than the planetary signal, introduce significant noise. Disentangling the tiny regular motion caused by Halle from the chaotic movement of the star required months of data and careful modelling of stellar behaviour. Combining the transit and radial velocity data allowed astronomers to calculate Halle's mass and radius, and therefore its density. The results showed that Halle is a gas giant, slightly more massive than Jupiter, about 1.3 Jupiter masses, with a size that matches a composition dominated by hydrogen and helium. Further analysis revealed no transit timing variations, suggesting Halle is likely the only significant planet in its system. Timing variations can indicate additional planets or moons, but in this case, Halle's orbit appears stable and solitary. Astronomers also searched for signs of Halle's atmosphere. During a transit, some starlight filters through the planet's upper layers, allowing the detection of molecules like water vapor or methane. Although no atmospheric features were definitively identified, these observations helped set upper limits on what Halle's atmosphere might contain. In a twist of scientific irony, the same stellar oscillations that hindered the planet's detection also provided valuable insight into 8 Ursae Minoris itself. By analysing the frequencies of these oscillations, a field known as astroseismology, astronomers confirmed that the star has already completed its red giant expansion. This finding made Halle's continued existence all the more baffling. The discovery of Halle was not just a triumph of instrumentation, but a testament to global cooperation. TESS provided the initial signal, but confirmation required observatories on multiple continents working in tandem. Theoretical models, software tools, and data archives, all built over decades, came together to validate what first seemed impossible. Looking forward, instruments like the James Webb Space Telescope and the upcoming extremely large telescopes will extend our reach even further. These tools may one day reveal the atmospheric chemistry of impossible worlds like Hala, or capture direct images of distant exotic systems. As TESS continues its steady watch, recording flickers of light from stars across the sky, it gathers the raw signals of possibility and impossibility. From a faint dip in brightness, measured across 530 light-years, came the evidence of a world that defies what we thought stars could destroy. The same tools built to find Earth's twins are now uncovering strange new planets that rewrite our understanding of how planetary systems evolve. Hala is a reminder that the universe still holds secrets, written in light, hidden in noise, and waiting for discovery. Chapter 10: Other Impossible Worlds. Across the Milky Way galaxy, scattered among the countless billions of stars that fill our cosmic neighborhood, astronomers have identified a growing collection of planets that defy the very rules by which we believe planetary systems should operate. Hala is not alone in its improbability. From scorched gas giants orbiting unimaginably close to their stars, to small rocky planets circling the collapsed remnants of stellar explosions, the universe seems filled with exceptions that challenge the foundations of planetary science. Take, for example, the planets that orbit white dwarfs, the dense, Earth-sized remnants left behind when stars like our Sun exhaust their nuclear fuel and shed their outer layers. These white dwarfs are stellar corpses, incredibly compact yet still glowing faintly with residual heat. Any planet that managed to survive the red giant phase of its host star should, by all logic, orbit at a great distance, safely removed from the deadly gravitational and thermal forces at play. Yet in the year 2019, astronomers discovered WD 1609-521b, a planet orbiting its white dwarf host once every 23 hours. Such proximity defies expectations. During the red giant phase, this region would have been engulfed in the star's expanding envelope, hot enough to vaporize any solid body. That this planet exists at all suggests our models of stellar death and planetary survival may be missing vital components, or that planets can somehow migrate into such environments after the chaos has passed. Equally perplexing are the so-called hot Jupiters, gas giants that orbit their stars even more closely than Mercury orbits our Sunday. With atmospheric temperatures soaring beyond 2000 degrees Kelvin, these planets are hot enough to melt metals and maintain exotic atmospheres filled with ionized gases and vaporized elements. According to conventional planetary formation theory, gas giants should form in the cold outer regions of stellar systems, where frozen water and ice grains provide the seeds for massive planetary cores to gather gas from surrounding nebulae. WASP-12b is among the most extreme of these hot Jupiters. It completes a full orbit in just over 1 Earth day and lies so close to its star that it is actively evaporating. Observations have revealed a massive trail of hydrogen gas streaming behind the planet, yet it stubbornly persists, losing thousands of tons of material each second and still remaining intact. It is a planet slowly erasing itself, but not yet gone. To account for hot Jupiters, scientists have proposed mechanisms involving planetary migration, scenarios where gas giants form at a great distance and later spiral inward due to gravitational interactions with other planets or with residual gas in the system. However, These processes are inherently unstable and often result in ejection or destruction. The presence of a stable population of hot Jupiters implies that such migration may be more common and more orderly than previously thought. More confounding still are planets orbiting pulsars, neutron stars formed from the collapsed cores of massive stars after supernova explosions. These pulsars emit regular pulses of radio waves, sweeping across space like celestial lighthouses. Supernovae are among the most violent events in the cosmos, releasing energy that should obliterate any surrounding planetary system. And yet, PSR 1957 plus 20 has at least 2 planets in stable orbits. These planets were discovered not by direct imaging, but through slight variations in the timing of the pulsar's radio pulses. Their orbital characteristics are so well defined that their positions and movements can be measured with microsecond precision. The very existence of pulsar planets forces astronomers to reconsider what kind of environments planets can endure or even originate from. One explanation for these extraordinary planets is that they are not survivors, but rather reborn. In this model, a second generation of planets forms from the debris of the supernova itself, coalescing from the remnants of a destroyed star into something entirely new. These worlds might contain exotic compositions enriched with heavy elements forged in the blast, offering conditions unlike anything found in first-generation planetary systems. Patterns are beginning to emerge in the catalogue of impossible planets. Many orbit stars that have undergone extreme transformations, expansions, collisions, or explosions, suggesting that stellar violence may not only destroy, but also create opportunities for planetary formation. From this perspective, chaos becomes a creative force, giving rise to planets in unlikely places. Transit timing variations have revealed even more unlikely systems, planets caught in delicate, chaotic orbital dances. One such system, Kepler 36, hosts 2 planets whose orbits differ by just a few percent. These close interactions generate gravitational resonances that, according to simulations, should destabilize the system over millions of years. And yet, the planets have remained in orbit far longer, suggesting a stability that current models fail to predict. Then there are the atmospheric impossibilities. WASP-96b maintains a stratosphere despite the extreme radiation it receives. HD 209458b shows signs of high-altitude clouds made from materials that, under normal circumstances, should not exist in such conditions. These cases challenge the very physics of atmospheric chemistry and dynamics. Some astronomers are now studying these anomalies systematically, searching for shared traits. It appears that certain types of stars, especially those with unusual compositions or binary companions, are more likely to host impossible worlds. Systems undergoing dynamic transitions, such as evolving giants or post-supernova remnants, also seem disproportionately represented in this group. Of course, selection bias plays a role. The strangest planets are often the easiest to detect. Hot Jupiters cause dramatic brightness dips during transits. White dwarf systems are relatively dim and thus easier to analyze, and pulsar planets are found through precise timing methods unavailable to normal stars. Even so, the consistent discovery of new anomalies suggests something deeper. Our theories remain incomplete. Understanding impossible worlds has practical implications for the search for life. If planets can survive, or even form, under conditions we once considered lethal, then the habitable zone may be broader and stranger than imagined. White dwarf planets might retain stable temperatures for trillions of years. Pulsar planets might possess energy sources that support exotic forms of chemistry and biology. In this ever-expanding inventory of planetary exceptions, Hala is one thread in a tapestry that continues to evolve. Each new discovery pushes the boundaries of what we believe a planet can be. The universe, it seems, is far more inventive than our current theories. It crafts worlds that resist destruction, defy physics, and redefine what it means to be possible in the vast, imaginative machinery of the cosmos. Chapter 11, The Lithium Anomaly. Deep within the spectrum of 8 Ursae Minoris, hidden among thousands of absorption lines that trace the presence of various elements, lies a chemical signature of ancient violence. The lithium abundance in this red giant's atmosphere is roughly 10 times greater than what astronomers would expect for a star of its age and mass. This enhancement is not just a scientific curiosity, it may serve as compelling evidence of a cataclysm that reshaped the system billions of years ago. Lithium holds a unique place in stellar chemistry. Unlike heavier elements forged in the cores of stars, lithium was created during the first few minutes after the Big Bang. That brief period of primordial nucleosynthesis produced small amounts of lithium, along with hydrogen and helium, when the universe was still a seething hot plasma. Since then, lithium has been steadily destroyed within stars, its fragility making it a rare survivor. At temperatures above 2.5 million Kelvin, lithium readily undergoes nuclear reactions when it encounters protons. These reactions destroy lithium by breaking it into lighter elements. This sensitivity makes lithium an unstable element in stellar interiors, vanishing long before heavier elements like carbon or oxygen are created. Thus, any significant amount of lithium found in a star's outer layers must have a special explanation. Red giants, such as 8 Ursae Minoris, should, by standard models, show extremely low lithium levels. As stars evolve and their outer envelopes expand, internal convection brings nuclear-processed material to the surface. Any original lithium from the star's formation should have been carried into the core and destroyed long ago. Yet, the spectroscopic data for 8 Ursae Minoris tells a different story. This anomaly was uncovered through precise, high-resolution spectroscopy. The lithium absorption line, located at 670.7 nanometers, is faint and easily lost among the stronger signals of other elements. Detecting it requires long exposures and meticulous calibration to eliminate interference from Earth's atmosphere and instrument noise. Dr. Chen's team at Peking University, using data from the SOFI spectrograph at the Haute-Provence Observatory, confirmed the lithium anomaly. Their measurements showed lithium levels approximately 2 decs above average, a dex being a factor of 10. This placed 8 Ursae Minoris among the most lithium-rich red giants in the galaxy. There are several theories that could explain this unexpected enrichment. One of the most compelling is planetary engulfment. As a star expands into its red giant phase, it may consume nearby planets. The outer layers of rocky planets, particularly their crusts, contain large amounts of lithium. When such a planet is absorbed into the stellar envelope, its material mixes with the outer atmosphere, potentially raising the lithium abundance. Models suggest that engulfing a planet with a mass comparable to Earth could raise the lithium levels by roughly the amount observed in 8 Ursae Minoris. However, this explanation introduces complications. Planetary engulfment should also elevate the levels of other elements, such as calcium and titanium, which are abundant in rocky planetary material. Yet 8 Ursae Minoris displays only modest increases in these elements, casting doubt on the engulfment scenario as a sole explanation. Another possibility is that a stellar merger occurred. In this scenario, 2 stars in a binary system collided and merged into a single object. During this violent process, lithium-rich material from the less massive star, particularly from its outer layers, could mix with the envelope of the primary star. This mixing might protect some lithium from the intense temperatures that would otherwise destroy it. Merger models suggest varying outcomes depending on the masses and evolutionary stages of the stars involved. Low-mass stars that are disrupted during a merger can contribute preserved lithium from their outer layers. In more massive mergers, lithium may also be synthesized in small quantities under specific nuclear conditions. However, such scenarios are rare and complex. In the case of 8 Ursae Minoris, the lithium signature aligns best with a merger involving a low-mass companion. The relatively quiet chemical profile, without the dramatic overabundance of many other elements, suggests a gentle merger that allowed lithium to be preserved without triggering widespread nuclear processing. Theories about lithium preservation have been further refined through 3-dimensional magnetohydrodynamic simulations. These advanced models show that magnetic fields within stars can facilitate complex internal mixing, transporting material between regions that are typically isolated in one-dimensional models. In certain conditions, this could protect lithium in specific zones and later dredge it to the surface. Clues about the star's rotational velocity offer additional evidence. Stars that undergo mergers often exhibit faster rotation, inheriting angular momentum from the orbit of the consumed companion. Measuring this through Doppler broadening of spectral lines could confirm whether 8 Ursae Minoris is spinning more rapidly than expected for a red giant, lending weight to the merger hypothesis. Yet timing remains a critical question. Lithium in stellar atmospheres is not permanent. It gradually sinks into deeper, hotter regions where it is destroyed. This means the event that introduced the lithium must have occurred relatively recently, within the last few 100 million years. This creates a puzzle. If a violent event enhanced the lithium, why does the nearby planet Hala still survive? A merger or planetary engulfment could have destabilized the planet's orbit or destroyed it entirely. The lithium anomaly has drawn broader attention across the field of stellar astrophysics. Large-scale spectroscopic surveys have revealed hundreds of lithium-rich giants, suggesting that dynamic events like mergers or engulfments may be more common than previously thought. Many of these stars share features with 8 Ursae Minoris: binarity, infrared excesses, or strange rotation rates, pointing to a broader pattern. Future observations may provide further clarity. By measuring isotopic ratios, such as lithium-6 to lithium-7, astronomers could determine whether the lithium was created in stellar processes or preserved from the early universe. Detection of other subtle abundance anomalies could reveal whether neutron capture events occurred, as might happen in certain types of mergers. The lithium in 8 Ursae Minoris acts as a chemical fossil, evidence of a hidden chapter in the star's past. Whether that chapter includes the destruction of a planet, the merger of 2 stars, or a rare kind of internal stellar process, it has left behind a trace written in atomic language. In the soft radiance of this aging red giant, lithium atoms still shimmer, a fragile remnant of primordial creation and cosmic upheaval. Their survival is remarkable, mirroring the unlikely endurance of Hala, the planet that orbits this turbulent star. Together, they speak of a history shaped by violence, mystery, and resilience, reminding us that the universe often defies expectation, leaving behind traces of events both destructive and strangely creative. Chapter 12: Planetary Resurrection. In the aftermath of a stellar collision, when two stars spiral into one another and tear themselves apart in a final fiery embrace, something extraordinary can rise from the wreckage. From this cataclysmic destruction, new worlds may be born. Planetary resurrection, a once speculative concept, now stands as a credible process in which the violent deaths of stars sow the seeds for planetary rebirth. It challenges our assumptions that planetary formation is a peaceful process tied only to youthful stars and calm, swirling disks. When stars merge, they do not simply vanish into one another. Enormous quantities of mass are ejected into space, rich in heavy elements forged deep within stellar cores. These stellar remnants, flung out at velocities of hundreds of kilometers per second, expand and cool, forming immense chaotic clouds of gas and dust. Rather than dispersing aimlessly, this debris is shaped and reclaimed by gravity, forming disks that might, under the right conditions, evolve into entirely new planetary systems. In the first few thousand years after such a collision, simulations show that debris forms concentric shells and turbulent spirals. Density waves ripple through the expanding material, creating clumps and ridges where dust can accumulate. These regions may eventually become the cores of second-generation planets. Temperature is a critical factor. Immediately after the collision, temperatures soar into the millions of degrees, hot enough to ionize atoms and vaporize any solids. But as the ejector expands, it cools dramatically. As it passes through specific thermal thresholds, atoms begin to recombine, molecules form, and eventually solid grains condense out of the cooling gas. These grains are the building blocks of planetary systems. Unlike the primordial disk that birthed our solar system more than 4 billion years ago, the material in merger ejector is chemically exotic. During the collision, core material, normally hidden deep within stars, is violently dredged up and mixed throughout the disk. Iron, nickel, and other heavy elements are far more abundant than in traditional planet-forming environments. This enriches the resulting planets with elements essential to rocky surfaces and magnetic fields. This enhanced metallicity dramatically accelerates planet formation. In typical disks, the scarcity of heavy elements limits how quickly solid cores can grow. It can take millions of years for a planetary embryo to accumulate enough mass to attract gas and become a giant planet. But in a debris field enriched by a stellar merger, dense cores could form in only a few 100,000 years. These rapid formation environments may favor the creation of super-Earths, planets larger than Earth but smaller than Neptune, rather than gas giants. The orbits of resurrection planets would likely be chaotic and distinct from those of planets formed in traditional disks. The angular momentum of the merger and the asymmetric spread of debris could lead to planets on highly elliptical or even retrograde orbits. Some may orbit at extreme tilts, while others could be locked in gravitational resonances, evidence of the violent conditions in which they formed. Clues to these resurrection worlds may be found in the chemical fingerprints of both the planets and their host stars. The isotopic composition of the debris can differ from that of normal stellar material, due to the extreme pressures and nuclear reactions during the merger. Planets formed from such material could display unique isotopic ratios, potentially detectable through atmospheric spectroscopy. The host stars themselves may retain signs of their turbulent histories. Surface enhancements of lithium or unusual element ratios could suggest past merger events. Stars like 8 Ursae Minoris, which show odd chemical compositions, may be examples of such stellar remnants, now stable, but having survived and reshaped themselves after a catastrophic merger. Disk formation following a merger begins quickly, within just a few centuries. Hydrodynamic simulations suggest that debris can settle into a disk within this short time frame. Once formed, planet formation may proceed over 1 to 10 million years, comparable to traditional disks, but under far more extreme radiation and magnetic conditions. Newly forming planets must survive intense energy output from the merged star. High-energy radiation can photo-evaporate atmospheres before they fully develop. Additionally, magnetic interactions between the star and ionized disk may drive fierce stellar winds, stripping gas and dust from the environment and altering planetary development paths. Observing these resurrection planets is exceptionally challenging. Unlike young stars, which glow with infrared signatures of planet formation, merger remnants can appear old and unremarkable. Their planets, too, may seem ordinary unless analyzed with high-resolution spectroscopy capable of detecting subtle isotopic differences or unusual orbital dynamics. Still, indirect evidence is growing. Statistical surveys of exoplanets around evolved stars show differences in orbital arrangements and compositions. If second-generation planet formation is common, we might expect to find more eccentric or misaligned orbits around chemically anomalous stars. Over time, patterns may emerge that point to planetary resurrection as a real and repeated phenomenon in galactic history. This possibility reshapes our view of the galaxy. If planets can form after stellar death, then life too might find a second chance. These reborn planets might harbour internal heat from radioactive isotopes, allowing subsurface oceans and geological activity far from their stars. They may also offer a surplus of life-essential elements, such as phosphorus and sulfur, concentrated by the same stellar processes that made their birth possible. Advances in observational tools may soon allow us to confirm the existence of resurrection planets. Instruments aboard space telescopes could analyze their atmospheres for unusual chemical signatures. Meanwhile, precise astrometric missions may detect the orbital irregularities expected from such chaotic formation histories. A combination of techniques, chemical, dynamic, and statistical, could finally reveal these hidden survivors of cosmic violence. The idea of planetary resurrection challenges the long-standing belief that planets form only once during a star's infancy. Instead, it proposes a galaxy where planetary systems are dynamic and evolving, capable of collapsing, exploding, and rebuilding themselves over time. From the ashes of stellar death, new worlds can rise. In the soft crimson light of 8 Ursae Minoris, we are left to wonder, is Hala an ancient remnant of a primordial system, or a phoenix world born anew from stellar destruction? Its survival hints at possibilities far beyond what current models can fully explain. Whether forged in the early days of the system or reformed after disaster, Hala stands as a testament to the galaxy's capacity for renewal. Planetary resurrection is not merely a scientific curiosity, it is a symbol of cosmic resilience. In a universe defined by entropy and collapse, it offers hope that creation is never truly finished. New worlds may yet arise from the remnants of the old, offering second chances for planets, and perhaps even for life itself. Chapter 13. What TESS revealed. 200 miles above the surface of Earth, the transiting exoplanet survey satellite, known as TESS, drifts silently through space, functioning with the steady precision of a cosmic metronome. Originally designed to find Earth-like planets around Sun-like stars, TESS has instead become humanity's most prolific discoverer of planetary phenomena once thought impossible. Launched on April 18, 2018, aboard a SpaceX Falcon 9 rocket, TESS was tasked with a mission of ambitious scope. Its goal was to monitor more than 200,000 of the brightest stars in the sky, looking for the subtle dimming caused when a planet passes in front of its star. Scientists hoped it would reveal thousands of new exoplanets, particularly small rocky worlds within the habitable zones of nearby stars, where liquid water and life might exist. The technical specifications of TESS showcase the power of modern astronomical engineering. It carries 4 identical cameras, each containing a 16.8 megapixel charge-coupled device. Together, these cameras provide a combined field of view measuring 24 by 96 degrees, enough to survey vast swaths of the sky simultaneously. Every 2 minutes, TESS records the brightness of hundreds of thousands of stars, creating a nearly continuous stream of high-precision data. The sensitivity of TESS is astonishing. It can detect changes in brightness as subtle as 20 parts per million, equivalent to spotting the extinguishing of a single candle in a stadium filled with 10,000 lights. Such precision is made possible by careful thermal controls that keep the detectors stable within mere millikelvins, as well as by sophisticated algorithms that remove noise introduced by spacecraft movement and environmental interference. Yet the world's TESS was built to find habitable, Earth-like planets have not been the primary source of its impact. Instead, TESS has unveiled an unexpected abundance of worlds that seem to defy astrophysical logic. It has found hot Jupiters orbiting their stars in a matter of days, super-Earths with densities implying unknown compositions, and most notably, planets like Hala, existing in places where survival should be impossible. One of the earliest such discoveries came from TESS's first year of observations, during its survey of the northern ecliptic hemisphere. The star 8 Ursae Minoris initially appeared unremarkable, selected only because its brightness made it suitable for high-quality data, but its light curve told a different story. It revealed periodic dimming events, indicating a planet orbiting far too close to its host star, an evolved red giant, for standard models of stellar evolution to permit. This breakthrough was made possible by a data pipeline that represents years of refinement. Raw data from TESS must first be corrected for instrument imperfections, such as nonlinear detector responses, cosmic ray interference, and scattered light from Earth or the Moon. Once cleaned, the photometric data is scanned by algorithms capable of detecting recurring patterns, isolating genuine planetary transits from stellar variability or instrumental artifacts. Detecting transits around evolved stars like 8 Ursae Minoris is especially difficult. These stars naturally exhibit oscillations, rhythmic fluctuations in brightness caused by acoustic waves inside the star. These fluctuations can mimic planetary signals unless properly filtered out. Only recently have software tools become sophisticated enough to distinguish between these two competing effects reliably. Whereas previous missions like Kepler focused on a single field of view for years, TESS surveys the entire sky over a 2-year cycle. This allows it to monitor evolved stars that are widely distributed across the sky, stars that are often brighter and closer than younger main sequence stars. In the case of Haller, TESS observed more than 50 separate transits, enabling precise measurement of the planet's orbital period and radius. The planet's size was calculated with an uncertainty of less than 5%, a remarkable level of precision. TESS's ability to conduct asteroseismology, measuring the internal oscillations of stars, provided the final confirmation that 8 Ursae Minoris had already gone through its red giant phase. These oscillations, which appear as subtle variations in brightness, follow predictable patterns based on stellar mass, radius, and internal structure. This gave astronomers definitive proof that the star had expanded and contracted, yet somehow its planet had survived. No previous mission combined such wide coverage, photometric precision, and stellar diagnostics in one platform. The result is a growing list of so-called impossible planets, worlds that survive in radiation zones, orbit white dwarfs, or exist within complex multi-star systems. These findings have forced a major rethinking of what planetary systems can look like. Originally, TESS was designed to locate potentially habitable Earth-sized planets. Now, it is reshaping our definitions of habitability itself. Planets have been found in locations once dismissed as sterile, including around white dwarfs and within the remnants of stellar explosions. Statistical studies of the TESS catalogue have shown intriguing trends. For instance, evolved stars appear more likely to host close-in gas giants than main sequence stars. This suggests that either planetary migration is more frequent in such systems, or that the processes of planet formation and survival differ fundamentally based on the mass and age of the host star. These trends are shaping new models of planetary evolution and challenging old assumptions. The high timing accuracy of TESS has revealed gravitational interactions previously undetectable. Transit timing variations, tiny shifts in the expected transit schedule, have exposed systems where planets tug on one another or spiral inward due to tidal forces. TESS has even uncovered planets that appear to be migrating in real time, providing rare glimpses into dynamic system evolution. The primary mission of TESS concluded in the year 2022, but its success ensured an extension through at least 2025. These additional years allow astronomers to detect planets with longer orbits, worlds that transit their stars only once every few years. The longer baseline will help determine whether worlds like Haller are rare anomalies or part of a broader population of planetary survivors. Test data will continue to drive discovery for decades. New machine learning algorithms are being trained to reanalyze existing light curves, searching for signals too faint or complex for earlier tools to detect. It is likely that many more strange and unexpected worlds remain hidden in the data, waiting for more advanced methods to bring them to light. The technological legacy of TESS will extend into future missions. The Nancy Grace Roman Space Telescope, expected to launch in the mid-2020s, will build on TESS's techniques for high-precision photometry, but will apply them to gravitational microlensing, another method for detecting distant planets. In its quiet orbit, TESS continues to monitor the sky, collecting photons that carry secrets from planets circling stars old and new. With each measurement, it adds to a growing body of knowledge that is transforming our view of the galaxy, not as a place filled with familiar systems, but as a cosmos overflowing with strangeness, creativity, and possibilities we have only just begun to imagine. Chapter 14: The Search for More. The discovery of Hala has ignited a new chapter in astronomical exploration, one dedicated to uncovering more impossible worlds that defy our understanding of planetary survival. Around the globe, observatories are being retooled, and new missions are being planned with urgency. At the heart of this effort lies a scientific truth. One anomaly is an outlier, but many anomalies suggest a hidden pattern. And in science, patterns demand explanation. The James Webb Space Telescope, humanity's most advanced space-based observatory, has turned its powerful infrared gaze toward systems like 8 Ursae Minoris. Its mission is to investigate how planets can survive in environments that, according to conventional models, should utterly destroy them. With unprecedented sensitivity and spectroscopic capabilities, Webb is now probing the atmospheres of worlds orbiting evolved stars, searching for clues hidden in their chemical makeup. In Hala's case, Webb's observations could reveal whether the planet's atmosphere contains unusual compounds or structures that allow it to endure. Possibilities include enhanced magnetic fields, exotic cloud layers, or unknown chemical processes that function as shields, deflecting the intense radiation of the host star and preserving atmospheric stability. Detecting any such mechanisms would not only explain Hala's survival, but also help identify other planets that may possess similar traits. Webb's coronagraphic tools allow it to directly observe planets orbiting nearby stars, those that are too faint or too close to their stars to be detected using transit methods. For stellar systems within 50 light-years of Earth, Webb might provide the first clear images of planets that have survived their stars' expansion phases, offering direct evidence of survivor worlds and their orbital configurations. Meanwhile, ground-based efforts are scaling up. The Transiting Exoplanet Survey Satellite, or TESS, has already compiled a list of candidate systems. These candidates are now being subjected to detailed follow-up using Earth-based telescopes equipped with ultra-precise photometry and spectroscopy instruments. These searches focus specifically on evolved stars and binary systems, stellar environments where planetary survival seems most improbable. In 2026, the European Space Agency plans to launch the Plato mission, which will extend the hunt for impossible planets further still. Plato's design prioritizes long-duration observations of Sun-like stars to detect smaller planets, but its capabilities also allow for monitoring red giants and other evolved stars. By continuously observing the same stellar fields for years, Plato may uncover planets with longer orbital periods, worlds that remain distant enough to escape destruction. The development of advanced ground-based instruments is key to this effort. The upcoming extremely large telescope, equipped with a 39-meter primary mirror, will offer the light-gathering power necessary to examine the atmospheres of nearby impossible worlds in extraordinary detail. Spectroscopic studies of these planets may uncover signs of exotic energy cycles, rare atmospheric compounds, or entirely new planetary processes. Machine learning is also transforming the search. Algorithms trained on vast astronomical datasets can sift through millions of light curves, identifying subtle anomalies that suggest unconventional planetary systems. These tools excel at finding what human eyes might miss, hidden relationships between stars and planets that hint at survival against the odds. White dwarf stars have become especially important in this work. These stellar remnants, what remains after stars like our Sun, exhaust their nuclear fuel, act as natural laboratories for studying planetary endurance. If a planet survives the red giant phase, it may be found orbiting a white dwarf. Several such cases have already been documented, including planets at extraordinarily close distances, implying either remarkable survivability or late-stage planetary migration. Detection methods for white dwarf planets differ significantly from those used for main sequence stars. Astronomers look for signs such as atmospheric pollution, where disintegrating planets leave detectable traces in a white dwarf's spectrum. Other methods rely on direct detection of dust and debris as planetary remnants spiral inward under tidal stress. Another surprising realm for planetary discovery is around pulsars, the incredibly dense, rapidly rotating remnants of supernovae. These objects emit highly regular radio pulses. Variations in pulse timing caused by orbiting planets allow astronomers to detect their presence with extreme precision. That planets can exist in such extreme environments, formed from stellar explosions, challenges even the boldest planetary formation models. The Square Kilometre Array, a next-generation radio telescope currently under development, will expand the sensitivity of pulsar timing techniques. With this increased precision, astronomers may detect smaller, more distant planets formed or surviving in the chaotic aftermath of supernovae. Gravitational microlensing represents yet another strategy. When a planetary system passes between Earth and a distant background star, its gravity bends and magnifies the background starlight. This bending can reveal the presence of planets, even those too distant to be found through other methods. The Nancy Grace Roman Space Telescope, scheduled to conduct an extensive microlensing survey, will be instrumental in detecting planets orbiting stellar remnants across the galaxy. Unlike transits or radial velocity methods, microlensing is especially effective at revealing planets at wide orbital distances, those most likely to survive stellar expansion. Theoretical models are rapidly evolving alongside observational efforts. New simulations now incorporate complex processes like mass loss, binary interactions, and orbital shifts during stellar evolution. These models help researchers predict where survivor planets might exist and what characteristics they might display, allowing telescopes to search more effectively. Chemistry also offers indirect evidence. Stars that have swallowed planets leave behind distinctive chemical imprints. For example, increased levels of heavy elements may indicate the ingestion of rocky bodies. By identifying stars with these chemical anomalies, astronomers may find systems where one planet was lost and others survived. Atmospheric models of planets orbiting evolved stars must now account for extreme radiation, dynamic heating, and unusual tidal effects, forces negligible in standard systems. These factors could create unique atmospheric conditions that, while hostile to life as we know it, may still support planetary stability. From an astrobiological perspective, the existence of impossible worlds has profound consequences. If habitable conditions can persist around white dwarfs for trillions of years, far longer than the main sequence lifespan of stars, then life may have more opportunities to emerge and evolve than previously thought. Collaboration is central to this field. Observational astronomers, theoretical physicists, and instrument developers must work together to unravel the mysteries of these systems. No single discipline is sufficient. The search spans continents, telescopes, disciplines, and data archives. Though current estimates suggest that planets like Hala represent less than 1% of all known systems, this number may be deceptive. selection effects and observational blind spots mean many such worlds could remain undiscovered. As survey technologies improve, we may soon learn that the universe is far more hospitable to planetary survivors than we once believed. The search continues, driven by the understanding that every impossible planet we find tightens the constraints on what is truly possible. Each new world is another data point that reshapes our theories of planetary formation and resilience. In a cosmos where death is routine, the survival of even a single world hints at unknown processes yet to be understood. Chapter 15: The Impossible Made Real. In the quiet halls of universities across the globe, textbooks are being rewritten. The discovery of Hala and other so-called impossible worlds has forced astronomers to confront a profound and humbling truth. The universe operates on principles more intricate and imaginative than previously conceived. What began as a puzzling anomaly detected by a single space telescope has transformed into a sweeping revolution in our understanding of planetary formation, survival, and endurance in conditions once thought to ensure their destruction. The existence of 8 Ursae Minoris b has upended decades of established astrophysical theory. For nearly a century, the prevailing belief was that planets orbiting dying stars faced only 2 inevitable fates. They would either be engulfed by their host star as it expanded into a red giant, or be violently ejected into the frozen depths of interstellar space. The discovery of a gas giant serenely orbiting well within the radius, where its host star should have reached maximum expansion, defies these long-held assumptions. This extraordinary configuration demands a complete rethinking of the evolutionary paths that planetary systems can follow. For generations, stellar evolution models were considered among the most refined in astrophysics, built upon observations and theory dating back to the early 20th century. Now, these models must accommodate mechanisms that somehow protect close-orbiting planets during the most cataclysmic stages of stellar death. The delicate interplay of gravitational forces, atmospheric dynamics, and orbital shifts that might permit such survival remains elusive, demanding new theoretical frameworks. We are now not only asking how planets perish, but daring to ask how they endure. The implications of these impossible worlds stretch far beyond individual planetary systems. They ripple outward to influence our understanding of galactic evolution and the prevalence of planetary bodies throughout the cosmos. If planets like Hala can survive the death throes of their stars more often than we assumed, then our galaxy may host untold numbers of such survivors, hidden worlds orbiting white dwarfs, neutron stars, and other remnants of stellar collapse. These populations remain largely undetected by traditional methods, which have historically targeted young, main-sequence stars like our own Sunday. Impossible planets such as Hala offer unique insights into the violent, transformative processes that shape star systems. Their atmospheres contain rare chemical fingerprints, elevated lithium levels, strange isotopic signatures, and exotic elements that hint at dramatic events such as planetary ingestion, stellar mergers, and even partial stellar resurrection. These chemical fossils serve as records of events that took place billions of years ago, preserving stories that would otherwise vanish into cosmic oblivion. For the field of astrobiology, the discovery of impossible worlds has profound implications. If planets can survive the death of their stars, some may retain temperate conditions for spans of time far longer than the main sequence lifetimes of their original stellar hosts. White dwarfs, in particular, can provide stable and long-lived sources of energy, potentially supporting life for trillions of years, far exceeding the current age of our own solar system, which is a mere 4.5 billion years old. Moreover, the enhanced abundance of heavy elements in some of these worlds may create favorable conditions for complex chemistry and, potentially, life itself. Second-generation planets, formed from the debris of previous stellar explosions or mergers, could contain far greater concentrations of biologically relevant elements than planets formed in the more chemically primitive early universe. These chemical advantages may counterbalance the otherwise harsh radiation environments near evolved stars, creating rare but viable sanctuaries for life in regions once presumed sterile. The appearance of impossible planets also exposes the shortcomings of current scientific models when confronted with extreme observations. None of our dominant theories of planetary formation, stellar evolution, or orbital dynamics predicted the existence of systems like Hala. Their discovery serves as a cautionary tale against over-reliance on limited observational data and the assumption that our current understanding is exhaustive. One of the central mysteries that remains is the statistical frequency of such impossible systems. At present, planets like Hala appear to constitute less than 1% of known exoplanets. However, this may be an illusion created by observational bias. As detection technologies advance, and as astronomers begin searching more intentionally in areas previously deemed unpromising, it is likely that many more such worlds will come to light. Machine learning algorithms, trained on massive astronomical datasets, are beginning to identify subtle anomalies that may reveal hidden populations of impossible worlds. These tools can detect patterns in stellar and planetary characteristics that human researchers might overlook. As artificial intelligence becomes more integrated into astronomical research, it promises to significantly accelerate the discovery of additional cosmic outliers. The challenge of studying impossible worlds has also pushed the boundaries of astronomical instrumentation. To investigate these planets, scientists have had to develop more sensitive spectrographs, finer resolution imaging systems, and more advanced data processing techniques. These innovations are not limited to the study of anomalous planets, but are enhancing our understanding of the universe across many domains. The international nature of this research has been equally transformative. No single observatory or research institution possesses the tools and expertise to fully understand these complex systems. The characterization of Hala, for instance, required the coordinated efforts of space-based observatories, ground-based telescopes, theoretical physicists, and data analysts across multiple continents. This spirit of collaboration is now becoming the model for tackling the great scientific puzzles of our time. Beyond the scientific ramifications, the discovery of impossible worlds invites us to reflect on the nature of knowledge itself. That such planets exist, despite our confident predictions to the contrary, reminds us that science is an evolving endeavour. It is a humbling lesson in the importance of intellectual openness and the willingness to revise even our most cherished models in the face of new evidence. As astronomers look ahead, missions such as the James Webb Space Telescope and upcoming extremely large ground-based telescopes are poised to uncover even more extraordinary systems. Each new discovery will bring us closer to a more complete understanding of planetary formation, survival, and the astonishing creativity of the universe. In the soft ruby glow of 8 Ursae Minoris, Hala continues its 93-day orbit, an impossible world made real. Somewhere in the vast reaches of space, others like it await discovery. Each of them is a silent challenge to our assumptions and an invitation to embrace the unknown. The impossible has been made real, and in that revelation lies the promise that the story of our cosmos is only just beginning. Thank you for joining us on this journey to the impossible planet Hala.